Alright, I believe we're good. Ready to go. Yeah. Hello everyone and welcome back to some more C Math Library. I don't know if I can call it that. I should probably come up with a better name. But today we're going to be finishing off the matrices. We'll be doing some more advanced matrix operations. So last time we looked at a bunch of scalar matrix operations and vector matrix operations and then matrix operations. Now we're going to look at matrix operations, so how to transform or how to manipulate a matrix to do certain functions or to give us certain results, stuff like that. Just a quick note before we start, I did commit a few things since the last episode. They were just I just added the other methods, the add matrix, the ones that were just repetitive, so they should be all in the GitHub. And then I also updated one of the new matrix method, which where was it? Come on, where is it? Here it is. So the new matrix, I just didn't. I just changed the size of the list here that we want to actually the value that was passed in, and then I also forgot to increment I every time, and every time I got a value. So those are the two fixes there. And then finally, in the preprocessor function, I forgot that you could not have argument types in the parameters. Though for some reason it did work when we tried it last time, but for now it has to be unsigned, or you just don't have any types in the preprocessor functions. Okay, enough of me rambling. Let's go ahead and start off. I'm going to go into OneNote, and we'll talk about the first. Oh, I need to update my Java. It's been coming out for a couple weeks, not a couple weeks, but a little bit. Okay, so I will drag this down. This is for later. The first one we're going to look at is something called a transpose of a matrix. And transpose is essentially taking a matrix and swapping its rows and columns. So if we had n and n by m, the transpose of this, denoted by a t in the top right, is going to... Is that the... Let me go shut my window real quick. God damn, it's still loud. That must have been also loud. Just smacked my microphone. I think... Yeah, okay. So the transpose of this matrix would give us a m by n matrix here. Like that. And essentially all we're doing is we're taking all the elements in the first row, and they become the first column. And all the elements of the second row become the second column. Stuff like that. So if we were to generalize this formula, we would say that the matrix A at in row I, J, the transpose at IJ is equal to a J comma I. So it's pretty much a reflection across the, or just you just swap the two coordinates. I believe that works. I could be wrong though. Let's actually see. If we had 0 0 or 1 1 1 2 1 3, then 2 1 2 2 2 3, this becomes 1 1 1 1 2 1 3 2 1 2 2 2 3. Is that right? The transpose at 1 1 is equal to 1 1. The transpose at 1 2 is equal to 2 1. Yeah, okay, that's right. So this is a general formula there for a transpose. We're essentially just taking all the coordinates and just swapping them. So in the code, and go all the way down. God, the documentation makes this shit super long. We'll just return a matrix, transpose, call the method transpose, and pass in a matrix pointer m. I'm passing the pointer just because I don't want to copy memory again. And then in matrix.c, this is 600 lines. God damn. We are going to say ret is equal to allocate mat, and we are going to pass in, for the number of rows, it's going to be the number of columns in the matrix that we want to transpose. So m.calls, and then for the number of columns, it's going to be the number of rows in the original. Then for unsigned int r is equal to 0, r is less than ret.rows, r plus plus, your classic, your nested loops that we've been using, or that we've had used so much. And then in the inner loop, what we're going to say is ret.elements at r at c is equal to m.elements at c at r. And then just return ret. If I were to run this now with, let's just say we had the matrix 2 we're looking at here. And I'm just going to say print mat the transpose of a reference to M2. And we'll see what we get here. Alright. I think that's right. Let's see, the first row is 6 3 negative 1 0, and the first column of the transpose is 6 3 negative 1 0 1 1 0 4 2 negative 2 5 0 2. Perfect. Looks good. Alright. So that's the transpose. Pretty simple. Now we're going to get into something more conceptual at first, but then it won't be too hard to implement in code. So our goal is to create a function that reduces a matrix to row echelon form. And I mean, this, if you haven't taken linear algebra or you don't know what matrices are, this is going to sound like I don't know, just complete, it won't make any sense to you, but essentially if we have a matrix, let's say 1 2 3 4, like that, and this kind of represented a system, like a system of linear equations. We would want to kind of get that to a form where we could do something with the numbers in the matrix. So that would involve subtract, or if you know basic algebra and you know about like solving systems of equations, if we had like 3x plus 2y is equal to 7 and 7x minus 1y is equal to 8, and you wanted to find the intersection point of that, you could just put this in a matrix that looked like this, and then if you row reduce this, you would get it to a form that looks like this, and then you would have an x and y for your intersection points. So essentially, I keep smacking my microphone. You can actually do this for any dimension of matrix, or yeah, essentially it's possible to do this for any dimension, and these rules are generalizable, and it's done through something called elementary row operations. So we're gonna have a few. We're gonna start by implementing or programming the elementary row operations, and then we will use those to actually create the reduced echelon form and row reduced echelon form. So for the row ops, these are just going to be operations on a row. There's going to be swap. That's simply just swapping two rows in a matrix. And what that would mean is if we had a matrix, let's say had R1, R2, and R3, just for the rows. If we swapped row 1 and row 2, it would be row 1 goes into row 2, and row 2 goes into row 1. If we added rows, we'll say R1 plus R2 goes into R1. This would just be adding R2 to R1. Alright, let me just... And then the adding rows would be... If we added R2 to R1, then we can multiply rows. So like KR3 goes into R3. This would look like... God, this is giving me such PTSD from freaking linear algebra. I can't... I mean, it's super useful, but like this is just straight up PTSD. And then you can also add multiples of rows. So R1 plus KR3 goes into R1. So that would look like plus KR3. So these are all elementary row operations that does not, and the thing that's special about these is they don't, if you perform them on a matrix, they maintain the integrity of the system. So for example, if we were to perform row operations on this system, we would get the same result. Like if, 7, 8, so this is our matrix. If we added R2 here, we would get a 10, a 1, 15, and then on the bottom would be the same. And this system would have the same set of solutions, essentially. So it doesn't destroy the integrity of the system. So we'll go through these one by one. Kind of want to blast through them just because these are going to be annoying to write out, but then they'll also allow us to do something a little cool with the swapping, especially. Alright, so let's go into matrix.h. And we will start. I need to put my tablet or my drawing tablet on. We'll start with the swap. So we'll return Boolean, swap rows, pass in a matrix pointer because we want to modify the matrix directly. Then we'll have an unsigned int R1 and unsigned int R2. I guess I could also implement this with references, but I'll just leave it with pointers right now. Then we'll have bool add rows, mat pointer m again, unsigned int R1 and unsigned int R2. Then multiply row, boolean again, multiply row, mat pointer m, unsigned int r, and float k. And then bool add multiple, mat pointer m again. Then we'll have an unsigned int r1, unsigned int r2, and then float k. Alright, let's get started. So I'm just going to paste the definitions in. and then I will just write them in a way that solves the problem. So for all these methods, we're gonna have to check for boundary conditions, and that's why I had return Boolean. So if R1 is less than, or if R1 is greater than or equal to M dot rows, or R2 is greater than or equal to M dot rows, return false. And I don't need to check for a lower bound because these are unsigned integers and therefore they cannot take negative values. I think I actually did that somewhere up here for boundary condition. Yeah, I did that in get mat row and get mat call, so I can actually just remove that. Or I'm now. Oh, this is tricky. One sec. Row minus minus. If we pass in a row 0 here, row minus minus would give us the maximum integer, so that would give us a positive, or it's greater than, so it's okay. But you can remove the lower bound on row. So when get mat row and get mat call, when we check for less than 0, you can just remove that condition, and that's good. Alright. God, there's so many methods to scroll through. Alright, for swap rows, we're going to want to swap each float, essentially. But instead of going through each float and swapping, what we can do is actually just swap the pointers, because remember, we have an array of pointers representing each row, so if we just swap the pointers for each row, that would still give us the same thing. So all we have to say here is for unsigned, or wait, no, I'm sorry, that's wrong. We can just use a swap method, which we could use to actually, which we could accomplish using a temporary variable, but you know, fuck that. I want to use something better. Let's use bitwise operations here. So let's go into cmathematics.h because we're going to create a general function that will help everyone. Void method. Swap, pass an integer pointer A and an integer pointer B. I will explain why I'm doing integers in a second. And then void swap float, pass in a float pointer A and a float pointer B. And then where do I want to define these somewhere. I'm actually going to see something here. Let's see if I can define bitwise or use bitwise operators in preprocessors. Bitwise operators. Ooh. Chapter 11. Oh, this is a course. God damn it. God damn it, O'Reilly. Preprocessor functions. I don't know if you can actually do that, to be 100% honest. Let me actually look something, or try and find an example, because I think I've done something similar before. Give me 2 seconds. Aha, okay. So we can define these functions in here by saying define swap And we'll pass in a how do we want to do this actually? You know, I will pass. I'm going to try this out. A and B. And then in the function, which I will define on multiple lines, so I have to use a backslash, we're going to say I actually don't know if this works, to be honest. Because I think these functions have to return something, so I don't think we can do this here. So I'll just create a new file called cmathematics.c. Just so we can define some of these standard functions here. So in cmathematics.c, go include cmathematics.h. And then paste the function signatures in. For swap integer, we're going to use a little bitwise trick here. And all it's going to be is we're just going to be bitwise XORing the values a couple times here. I explained it more in a let me find this real quick. A long time ago, 6 months ago actually, when we did bitwise operators. Right here, this is the swapping function. It essentially just takes the XOR and flips values without a temporary variable. So essentially all we have to do here is just bitwise XOR a couple times. So you have to dereference A, and then bitwise OR it. Bitwise OR equal with the dereference of B. Then the dereference of B is equal to the dereference of A XORed with the dereference of B. And then dereference A XOR equals dereference of B. And then for swap float, all we can do is actually just call swap and then just convert or cast the float pointer to an integer pointer, because remember, these are still just pointers. Oh wait, integer pointers, sorry. Let me actually try, because I want to see something here. Does that work or no? No, it doesn't like that. Because I don't think this, I think if we do it this way, we're going to have to actually go through each value, because this dereferences it. So get the first value that it's pointing to. But let me see if this works actually. I doubt it will, but I'm hopeful. So for swap rows, all we have to say is swap float, pass in m dot elements at R1 and m dot elements at R2, and then return true. Alright, let me test this out. So all we did here was just did it not like this? Did I misdefine something? Oh, I didn't put a pointer for the second argument in swap floats. There we go. Yeah, there we go. So all we're doing is we're just swapping the pointers here, but I don't think this will actually work. And I'll explain why in a second, but let me see what happens here. So swap rows, a reference to M2, and I will swap 2 and 3. Oh, I actually have to add that we're counting from 1 again, so I need to subtract 1 from R1 or decrement R1 and R2. Just because we're counting from 1 again. There we go. All right. That's big. I don't think it's gonna like this. Undefined reference to, oh, because that's right, I need to add the cmathematics.c to the build path. So cmathematics.c to the batch file that compiles this. There we go. God, this album is fucking amazing. It actually slaps. Yeah, I'm not seeing anything swapped. But I think something... Oh, but probably... Yeah. Oh, wait. Oh, I didn't print it again. Let's see. Yeah, I think it just swapped the first two values as is expected. Because essentially, in swap, what we do is we dereference the values, and then we just bitwise OR them. So that's just going to be swapping the values that are stored there, but not the pointers. Because if you think about it, we're passing in the pointer to a row, which is just a pointer to the first value in the row. But when we dereference that, we only get the first value in the row. So maybe... Let me see if there's a way to swap values. C swap pointers bitwise XOR. No, I don't want to swap two numbers. I want to swap pointers. There we go. Swap two pointers. There are no bitwise operators on pointers. Huh. I don't really... Okay, I guess I just have to, here, I'm just going to try C swap pointers. Swapping pointers, Alright, so I think I'm just gonna have to create pointers, or a temporary pointer, I'd say, because I don't think there's any way to do this, like using bitwise operators on pointers. So we're gonna have to create a temporary one. So I'll create a new, I'll keep the swap functions here though, just because, and then we'll have void swap pointers, or I'll say swap float pointers. Pass in a float pointer A and float pointer B. Or you know what, I feel like this would be more suited to the matrix. Just doing this in the matrix, in the swap rows function here. So float pointer TMP is equal to mat dot m dot elements at R1, then m dot elements at R1 is equal to m dot elements at R2. and then m dot elements at R2 is equal to m dot elements at R1. And this should swap the pointers to the rows. Maybe this will work. That just copied it over. Oh, because I assigned it to itself. Okay. So m dot elements at R2 is equal to temp now. And now that should work. Yep, it worked. Okay, perfect. So yeah, this is just a very simple. I feel like this is, you learn this in a like second day of comp sci class, where you have a temporary variable, but here with the temporary variable is actually the reference to the row. So we're just swapping the references, and that will swap the rows in essence. But it won't swap the values. It won't interchange the values in each memory location. It's only changing what the array of rows points to in order. If that makes sense. All right. Now for add rows, this is going to be a little different because we're going to have to actually iterate through. First, once again, boundary conditions. Well, subtract one or decrement R1 and R2, then boundary conditions. You can just copy and paste that from above, and then we just want to iterate through each column. So for unsigned int c is equal to 0, c is less than m dot calls, c++. Then m dot elements at R1 at C plus equals m dot elements at R2 at C. So we're just adding the elements from the second row in the corresponding column to the first row, or yeah, to the first row specified, and then return true. I can test this here. Add rows. Run. 1 plus -2 is -1. 6, yep, good. Multiply row, same kind of deal. You can actually just copy the definition, except this time actually don't copy that the definition from above, because we have different names. So this time we only need to decrement R, then have the boundary condition only for R. If R is greater than or equal to m dot rows, return false. Otherwise, we're going to iterate through the loops, or through the columns. For unsigned int c is equal to 0, c is less than m dot calls, c++, m dot elements at r at c times equals, and we're going to use the k there. And actually, k cannot equal 0. So if r is greater than or equal to m dot rows, or k is equal to 0.0 float. And then just return true. I'll try this now. Multiply row, reference to m2, we'll multiply row 1 by 2.0 float. 12, 6, perfect. Add multiple kind of combines the two last methods. So we need to decrement R1 and R2. Then boundary conditions is if R1 is greater than or equal to m dot rows, or R2 is greater than or equal to m dot rows. And then also or k is equal to 0.0 float. Return false. If k was 0 here, it would not modify anything, but we're just going to return 0 either way because it doesn't accomplish the operation. Then we're just going to do kind of the same thing, iterate through each column. For unsigned int c is equal to 0, c is less than m dot calls, c++, m dot elements at R1 at C plus equals m dot elements at R2 at C. And then I forgot another boundary condition here, is the rows cannot equal themselves. So we have k is equal to 0. We have the two rows are too large, so the values for the rows are too large. K is equal to 0, but then the rows cannot also, you cannot add a multiple of a row to itself. I believe. Yeah, you cannot. So or R1 is equal to R2, and then or just like that. And I will also have to add this to the other methods too. Oh. And then add this to add rows. So if the rows are equal in add multiple, add rows, or swap rows, then just return false. Like so. What the fuck? Oh. Okay, perfect. Alright, let's try this one. Add multiple. Oh, I didn't add multiple, I didn't multiply it by k. K times m.elements at R2 at C. Now if we run, we should get 6 plus 2 is 8, 3 plus 2 is 5, negative 1 plus 0 is negative 1, and 0 plus 8 is 8. Perfect. Alright, so those are all the elementary row operations that we have. And now, what we're going to do is we're going to combine these row operations to actually get to row reduced echelon form, or row echelon form. This is the algorithm here, so I'll actually just go over what row echelon form is. We'll start with row echelon form, and then we'll do reduced row echelon form. Row echelon form gets its name from its staircase form, so this I should probably draw out. Okay. So with RREF, or reduced echelon form, it kind of has this cascading structure, so echelon. Something like that. Essentially, there are 3 basic rules. All 0 rows have to be at the bottom. The first non-zero entry from the left in each row is a 1, so that's what you get here. That's why it's cascading. And then each leading one is to the right of the leading ones in the rows above. So the first non-zero entry, it will have to be a 1, and that's called a leading one. So, and then in every row below, the leading ones have to be to the right of that. So it gives you this echelon structure. And then once again, you have a matrix. You can get to row echelon form simply through the Gaussian elimination, which is just essentially a combination of elementary row operations. So what we have to check for is if the matrix is all zeros, then it's in row echelon form. Otherwise, we're going to find the first column from the left containing a non-zero entry and move it to the top. Or wait, is that right? Or is it the first row? Yeah, it's find first row from the top. And we're going to do this for each column. So find the first column, or first row from the, you know what, one sec. Row from top. So for each column, we're going to find the first row from the top containing a non-zero entry and move it to the top. So swap it Then we're going to multiply that new top row by 1 over a to get the leading one. Then we have to subtract multiples of that row from the rows below it to get the zeros, because each leading one has to have zeros underneath it. And then repeat the steps on the remaining columns. Yeah. And then reduced row echelon form will just be an extension of that. Alright, so to implement this, we'll have a header. And once again, I will just have the void REF and pass in a matrix pointer M. And then in matrix.c, I'll just put the signature again. So we're gonna have a variable to keep track of the current row. Sorry, God damn it. The reason why we're gonna have to do this is because as we progress down, we don't want to modify the upper rows or the columns in the upper rows, and we want to focus in on the rows or on the column. Or sorry, when we keep going to the right, we want to focus on the lower rows. So we want to keep track of the current row that we're looking at right now. Then we're gonna iterate through the columns. For unsigned int c is equal to 0. C is less than m dot calls c++. We're going to say unsigned int r is equal to current row. And then if r is greater than or equal to matrix or m dot rows, we're going to break. The reason why is because once we get through, let's say that we didn't get through all the columns and we already got into row echelon form. So let's say if there were more columns than rows, we don't want to keep going because it's already in row echelon form, so we'll just break out of the loop. Then we want to find the non-zero entry. So for empty first condition, or empty first entry, r is less than matrix dot rows, r++, and then if matrix dot elements at r at c, or sorry, m. God, I used the name matrix in my reference here. So if m dot elements at r at c is not equal to 0.0 floats, we want to break out because we have found the first non-zero entry. If we didn't find one, then it's a column full of zeros. So if r is equal to m dot rows, then we have not found a non-zero entry, so we can just continue on to the next column. Then we're going to swap this with the proper row. So swap with proper row. So if current row does not equal r, or we can actually just call swap rows mat or m, then current row and r. So the row with the first non-zero entry in the column should be moved to the current row. So we want to kind of be working at the top there, because once again we want to clear out the zeros underneath the leading one. Then we're going to multiply the row by the value, or by 1 over the value. Multiply row by 1 divided by value. So we're going to have a placeholder called float factor is equal to 1 divided by m dot elements at current row at c. So just get the factor here, because we're going to be using it twice. Or will we? Well, we're going to be using it several times, so I don't want to recalculate it every time. So for unsigned int call is equal to c. Call is less than matrix dot calls. Call ++. Wait. oh yeah, so we're multiplying the row by 1 over the value. We could use the multiply row function that we have, but since we're not going to be multiplying any of the zeros by the value or anything to the left of the leading one, we're just going to simplify and reduce some running time. So m.elements at current row at call times equals factor. Once again, we don't need to worry about anything to the left because they will already be zeros. Then we want to clear out the rows below. So for r is equal to current row plus 1. R is less than m dot rows, r plus plus. We're going to add a multiple. Matrix R is going to be the first row that we're going to be adding to. Then current row will be the multiple of the row that we're adding to, and then the factor or the multiple will be -1 times m dot elements at R at C. So essentially what we want to do here is just add to clear out all the values down below the leading one. I'm explaining this really shittily, so if you want to watch a video on this, there's plenty out there. I'll find a link for one. But essentially we're just going to be subtracting multiples of, and since there's a 1 in the current row, if we just say -1 times the value in the row that we want to clear out, we're just going to be subtracting the value from that, which will just get us to 0, which is what we want. And then after the loop, we want to increment current row. Alright, so that is row echelon form. Pretty good. It's easy to implement on the computer. So let's try this. I'll get an example here. Row echelon form example. Come on, give me an example. No, I don't want reduced. Is this it? Alright, let's watch this dude's video. The Digital University 2011. Holy shit.
This is our first.
Alright, I don't want to listen to him. That was mean, but I just want to get through this. Okay, so we have our matrix. I will just move this over and I'll go split screen. So our system mat m is equal to matrix with 3 rows, 4 columns, and then for the values we're going to have 1.0, 2.0, 1.0, 3.0. 3.0, -1.0, -3.0, -1.0, then 2.0, 3.0, and 1.0, and then 4.0. Damn, I was mean to this dude. He's definitely...
In row echelon form, it breaks down. But the way the system breaks down tells us something very important about matrices, and that's a lesson that we're going to use over and over again throughout the rest of the videos.
That's super valuable. All right, let's do this. Print mat m REF reference to m, and then print mat again m. All right, let's run this. Did we get that? We did. Oh, that's not right. What the okay, no bueno. Let me refill my water and then I'll debug. Give me a second. because that's not right at all. So potentially what I'm thinking is this is it's not subtracting it from all the rows. R is equal to current row plus 1. Let me try printing out the matrix at each step. How about that? Alright, what do we get here? That's our original. Alright, so yeah, that's the original right there. What I'm really confused about is that it doesn't... Let me debug this real quick. We will break at matrix.c at line 691. Run. Okay. All right, step 4 unsigned. Yep, good. Oh, damn it. You know what, I stepped into the function. That's unfortunate. Alright, unsigned in R is the current row. R is 0. Alright, now we're in the loop. Alright, so we found that the element, the first non-zero entry was that one. Good. Step out again. If R is equal to m rows, then we didn't find one, but we did, so that will not. Alright, let me do this here. Alright, so this should just break out immediately. Oh, I think I know why. Because we're passing in the starting counting from 0 for the swap rows here. That makes a lot more sense. Damn it. You know, I'm starting to think that this counting from 1 is not fun. Let me just get rid of the counting for 1 for now. Or from 1 for now. Just to see if it makes it any better. No, it still gave us the fucking same thing. Oh wait, no, that's right. Maybe what? Is that right? 1213 is good. You know, let me whip out. I'm gonna whip out my calculator. Got my handy dandy TI-84. Second matrix, math, REF. It's 3 by 4. We're gonna have 1, 2, 1, 3, 3, negative 1, negative 3, negative 1, 2, 3, 1, 4. Hey, no, wait. Oh wait, I think that that's still valid though, because you know, let me just check this dude's. Sir, fuck. Alright, this is right. This 1 and 4, that's right. But I believe that the TI-84 uses a weird algorithm here. Because a matrix can have multiple row echelon forms, but it cannot have different reduced row echelon forms. So let me test this out. So -7, if we were to get to this form, we would have to take -6 divided by -7, which is 0.857, good. Then -10 divided by -7 is 1.42, perfect. Apart from that, I think we're good. Yep. Alright, so this is right. Awesome. Alright, now that we've done row echelon form, implementing reduced row echelon form is not... Let me turn this down a little bit. Is not too difficult. So if we go into matrix.h, I'm going to create another definition here called reduced row echelon form. So RREF, pass another pointer matrix. Alright. Paste the thing in. And in this function body, you can actually just copy everything from reduced or row echelon form. The only difference in reduced row echelon form is that in reduced row echelon form, the leading one is the only non-zero entry in the entire column. So that means that we have to clear out the zeros from not only below, but also from above the leading one. So instead of only going from current row to the end, we have to go from 0 to the end and just clear out all the zeros. So for clearing out rows below, or just clearing out, so the last for loop before we increment current row in the column iteration, just delete that and say clear out rows below and above, or above and below. And then we're going to iterate for r is equal to 0, r is less than m dot rows, r plus plus, and the only row we don't want to clear out is the current row. So if r is equal to current row, continue. And then add multiple. It's just the same statement. Pass an m, r, current row for the second row, and then the constant will be -1 times the value in that row. So -1 times m dot elements at r at c. Once again, same theory of just clearing out the value. Since the value in the current row is 1, we just need to multiply that 1 by whatever is in the second row to clear it out. Alright, now if we call reduced row echelon form, we should get the same answers, because there's only there's one unique reduced row echelon form for every matrix. Okay, so that is, so we're getting a 3, -2, and 4, which is, I can't read this, I'm sorry.
So,
oh, wait. X3 is equal to, that's a 4. Well, what's X1?
back, join us for the next video. We'll consider our
X2 is -2. Come on, dude. Did he probably, oh, he did up here, okay.
real easy to solve the
Oh my god, it's right. 3, -2, 4. Fuck yeah. Atta boy. Nice. Okay, so that was reduced row echelon form and row echelon form, and elementary row operations, which will be very valuable just all around in linear algebra. So if you ever do take linear algebra, or you have taken, you will or you do know how important the reduced or this algorithm is, which is, so it's cool that we implemented it in code. And like I said in a couple videos ago, matrices are super important for data analysis. So if we have this code running on a low-level machine in like a hospital or something, it would be able to do that quickly, which is good. Okay, now I'm gonna do something else, or move on to the second topic, which is somewhat related here. It's called augmentation. So the idea is, if we have a matrix, we can augment it by another matrix that has the same number of rows to produce, let's say we had a bunch of these. And we could produce a larger matrix that looked like this. So it just had the columns augmented on at the end. Yeah. So essentially, I mean that's pretty much all there is to it. You can also add vectors on it, or augment vectors at the end, which is cool. The only condition is that the number of rows is the same. So we'll have two functions here to augment a vector, which we will do first since it's easier, and then we'll augment the matrix. So I will have a return type matrix, matrix, then augment vector, pass in a matrix m, matrix pointer m, and then a vector pointer v. And then I'll just define the other function too, or write the signature. Return matrix, augment matrix, pass in a matrix pointer m1 and matrix pointer m2. Or let's do matrix pointer m, so the format will look similar, and then matrix pointer m2. Alright, copy those signatures, paste them in matrix.c. 774 lines. God damn it. Okay, so for the vector, once again we have to check for the, the number of rows. So if m.rows does not equal v.dimension, because if we're just going to consider the vector as a column matrix, and we don't want to kind of convert it over, we can just check if the dimension of the vector is the same as the number of rows. So if they are not equal, we are going to return mat undefined, and then to actually do this, we're going to have to allocate something. Allocate a new matrix, so mat ret is equal to allocate mat, same number of rows, so m.rows, but this time for the columns we're going to say m.calls plus 1, and we can just say plus 1 for now because the vector will only be one column. And all we have to do is we'll start just by copying the matrix values over. So for unsigned int r is equal to 0, r is less than ret.rows r plus plus, and for unsigned int c is equal to 0, c is less than m.rows. Make sure that, or we can just use m.rows and m.calls actually. And then c++, And all we have to say here is ret.elements at r at c is equal to m.elements at r at c. So this is just a direct translation over. And we can't use the copy function because we want to expand the dimension. And then now what we have to say is at the end or after the for loop here, we're going to say ret.elements. So after the inner for loop, so we're still going to be in the row. So ret.elements at r at we will say how do I let's make the column value unsigned int c just a variable in the inner loop so we can access it outside, and then we'll say at r at c is equal to v.elements at c, and we can use the column value here just because it will be added to be the number of columns in the input matrix. So when we have the last matrix, it will be at index c. So let's try doing this now. So I have the matrix, and then I will allocate a vector. So vect v is equal to vector. I'll pass in 3 values. So 1.0, 2.0, and negative 5.0. And then augment vector. Pass in a reference to m, reference to v, and then print the matrix m again. Or let's say mat m2 is equal to that. And I'll run this, and it is now, that is not right. It didn't like this. Oh, I didn't return red, that's why. Okay, that makes sense. Oh, it didn't like the values. That's weird. Let me try printing the vector. See if there's a problem there. What? No, the vector looks good. What the fuck? Oh wait, sorry, this should not be v.elements at c, it should be v.elements at r. I'm sorry. Yeah, that makes more sense. So once again, when we're assigning to r at c, it should be v.elements at r. Now it's good. 1, 2, negative 5, perfect. Okay, so we're going to do something similar for augment matrix. So I'm actually just going to copy the definition over. But now we're going to have to do something a little more trickier, I'm going to say. Thank you, Hans. I appreciate that. Yeah, it's pretty cool. I did not expect this shit to go this far, but I guess it has. And now I'm on the road to 500 million subs. I'm knocking on the door of that. Like it's unprecedented how close I am to 500 million subs. It's quite amazing, actually. It's quite amazing. Yeah. Alright, let's so back to this shit. What was I doing? The fucking oh yeah, we're augmenting the matrix now. Okay, the check in the boundary conditions in the top needs to be that m.rows has to equal m2.rows, otherwise return the undefined matrix. Or m2.rows. And then after the first inner for loop, we're gonna have a second one. We're gonna have another loop here. For empty first condition, c is less than. We're now gonna say ret.calls, then C++. So once we've actually exhausted all of the values in the current row of the original matrix, we still have space allocated in the return matrix, which we have to actually extend. So it's the number of columns in the ret matrix will be m.calls plus m2.calls. Because now we're augmenting a whole nother matrix on the end. So right here we have 3 columns, then 2 columns, and then the augmentation has 5 columns. So in the second loop, we're going to say ret.elements at r at c, we're same assignment location, is equal to, yeah, it is exponential growth. God, this, I feel like the delay is super freaking laggy, or it's just, there's hella delay here. I don't know. I guess normal latency like has this shit going like a minute behind maybe. I might have to fix that, but I don't know. Yeah, so the returns, the return matrix, it has a value RC, and this is going to be equal to m2.elements at r. So we're going to, because the row is going to stay constant, but this time we're going to say c minus m.calls. So we're just subtracting the number of columns in m, and I will actually diagram this out real quick. So if we called augment, so if this is m and this is m2 and we called augment on it, we're going to say for r goes from 0 to 3. When r is equal to 0, we're saying that ret at 0 is equal to this. Then at 1 is also equal to this. I'm just taking the first row of the original matrix, and then at 2 is equal to this as well. Now, after this loop, we have to loop through the values in the second row, or in the same row of the second matrix. So values in third column of the return, or the fourth column rather, is going to equal to an x, but this is going to be equal to m2 at 0 at 0. So we have to take the 3 and subtract the number of columns in the first one. So this is equal to 3 minus m dot rows, or dot calls. So we're kind of creating an offset here. Okay, so that should work. Let's try it now. Main.c. So we'll create mat m2 is equal to matrix, let's say 3 rows, because it has to have 3 rows, and then we'll say 2 columns. What values do we want? Well, let's do 5.0, 7.0. Then the second row will have negative 16.9 and 2.14. Then the third row, I don't know, negative 72.4. Let's get real wild now. How about 3,926.783 float. That's a crazy value. Holy shit. It might, honestly, this might just break if we do that shit. Let me print this out, and then we'll say mat m3 is equal to augment matrix, reference to m1 and reference to m2, print mat m3. let's run this. 1, 2, let me just get this bigger. 1, 2, 1, 3, good. And the 5, 7, looking good. Fuck yeah. Alright, that's augmentation. Pretty simple. I mean, a good exercise, I'd say, to look at, but also pretty simple. Now for the final thing that we're going to do today is the determinant. So this is going to be more of a thought-provoking exercise, and I will bring my tablet back again. So for the determinant, if you don't know what that is, it only works on square matrices. So if we get a square matrix, and this works in any dimension. Let's say we had 1, 2, 3, 4, 5, 6, 7, 8, 9, or let's actually make it 4 by 4 just for demonstration. So that's our matrix, and let's say we wanted to find the determinant of this matrix. So what you do is you do something called cofactor expansion, and once again, I'm not going to go too deep into why it works, but it's essentially just the definition. But you're going to expand across one row or one column. We'll just use the first row, just because, and then you essentially take each value, and then you take the determinant, you multiply that value by the determinant of the smaller square matrix that doesn't have the row that you're clearing on and the column that the current value is on. And this also works for if you want to clear across a column. So the smaller matrix would not have the column that you're clearing on and the current row of the value. So this is going to be equal to 1 times the determinant, which is denoted by the vertical bars of 6, 7, 8, -1, -2, -3, -5, -6, -7, and you can just smell the recursion on this. Like it's so, the recursion is just tingling. My recursion senses are just tingling right now. It's ridiculous. And then we're going to do this for the next value, but you also have to alternate signs. So -2, then the determinant of 5, 7, 8, 9, -2, -3, and -4, -6, -7, and this time we are excluding the second column. And you do this for the next two values as well. And then you might be wondering, well, what's the determinant of this matrix? Is it the same thing? And yes, it is. So we'll clear across the first row again. Take the smaller matrix. So this is equal to 1, and then a 6 times the determinant of -2, -3, -6, -7, and then -7, blah, blah, blah. But then, what do you do in the second matrix here? Well, it turns out that the 2x2 matrix is the base case in this recursion case here. So if we had a 2x2 matrix, A, B, C, D, this is just going to be equal to A times D minus B times C. And that's where you would stop in the recursion, essentially. So this would become 1 times a 6 times -2 -7 -3 -6. Stuff like that. So yeah, you can see how the recursion is actually like directly applies to this. Yeah, so we're gonna have to implement two methods: one helper method and then the actual determinant method. So go back to matrix.c, and we're gonna have a matrix called, or a function called splice matrix. returns matrix, and we're calling splice matrix. Pass in a matrix pointer m, and then a row to exclude. So unsigned int exclude row, and unsigned int exclude call. God, my freaking sinuses are full right now. I just, I can barely freaking talk. I probably sound as if like I'm trying to lower my voice, but I physically cannot create enough of an airway to talk. It's kind of funny. Shit, I don't know. I probably have corona. You never know. Oh shit, am I gonna get banned for saying that word? Might. Oh, you know what it is? It's Thanksgiving. Oh fuck, I didn't say Happy Thanksgiving. Happy Thanksgiving. I never said that. I completely forgot. But yeah, Happy Thanksgiving to everyone. Hope your turkeys were stuffed nice and plump. And then also, I hope you used a matrix to actually analyze the recipe for the turkey. And how to do that, I actually have zero fucking clue, but use the matrix. Or fuck, I just created an unintentional crossover. You can just bend the turkey using your will, because we exist in the matrix. And that's what I meant to say. I didn't mean to reference Star Wars there, but for splicing this, we are going to I think this is pretty straightforward. We're just going to be taking a value, or we're just going to be iterating or going through the matrix and then just skipping over the values in the exclusion row and the exclusion column. Yeah. So we will count from 1 again. So exclude row minus minus and exclude call minus minus. I will, once we're done with this, I'm going to try and find a way to use that in the elementary row operations. So mat ret is equal to allocate mat, and the number of rows will be m dot rows minus 1, and we're subtracting 1 because we're excluding 1 row, and then the same thing for the columns. M dot calls minus 1. Then we're going to have an offset for the row. Unsigned int row offset is equal to 0, and this will be increased to 1 once we cross over the exclusion row. So the reason why is because we're just going to be once we pass over, or I'm just going to take, I need to draw this out again. It's easiest to explain there. Let me actually just copy this matrix here. So if we were splicing and we wanted to exclude the second row and the third column, third row, second column, sorry. We would call splice mat, or a reference to mat, and then the third row, second column. And essentially the return is going to be a 3 by 3. Since this is 4 by 4, we're going to subtract 1, so it's going to be a 3 by 3. So what the return is going to look like is 1, 5, -4, 3, 7, -6, and then 4, 8, -7. That's going to be the spliced matrix there. And so the element in the top left is 0, 0. That's good. But the element in the bottom left is going to be 2, 0, which maps to 3, 0 in the original. So once we cross over the row that we want to skip, we essentially just want to create an offset to access one element further or one row further in the original matrix. Okay. For unsigned int r is equal to 0, r is less than ret dot rows r plus plus. And then we're going to do the same thing for the column, except the column offset has to be reset every row. So unsigned int call offset is equal to 0, and then if r is equal to exclusion row, we're going to say row offset plus plus. And this could also be, the reason why I'm doing plus plus not is equal to 1 is because if we want to expand this to have multiple rows excluded, we could pass in an array, and then we would be able to just do that there. Alright, and then now we're going to iterate through the columns very similarly. For unsigned int c is equal to 0, c is less than ret dot calls c plus plus. If c is equal to exclusion column, call offset plus plus. And then ret dot elements at r at c is equal to m dot elements at r plus row offset, and then at c plus call offset. So we just need to add the offset when we're accessing the element from the original array, or from the original matrix. And then return ret. Okay, we can test this out now with our matrix. So let's actually just use the augmented matrix here and say mat m4 is equal to splice mat, pass in a reference to m3, and we will do the second row, third column, and then print mat m4. Okay, so we have, in the original, we have 6 columns, 3 rows, and in the spliced we have 2 rows and 5 columns, which is good. And we have the first row is the first row, and then the second row in the spliced matrix is the third row of the original, which is good. And then for the columns, we spliced the third column. So we should not see a 1, -3, 1, which we do not, which is perfect. Awesome. Alright, so yeah, this splice here, you kind of see how this directly lends to getting our determinants here. Because if we just splice, we have to splice this matrix every time we want to get the determinant of the smaller matrix. Yeah. Okay, back to matrix.h. We're going to return a float for the determinant. Pass in a matrix pointer m, or just matrix m. Then in matrix.c, you can copy the signature over. Once again, conditions. So if m.rows does not equal m.calls, return 0.0 float, because you cannot find the determinant of a non-square matrix once again. Then we're going to have our base cases. Technically, here, let me see what the technicality is for a 1x1 matrix. 1x1 matrix determinants. Alright, it's just the value, okay. So if m.rows is equal to 1, and we don't need to check for columns because we know they're equal, so if the rows is equal to 1, then the number of columns is equal to 1. So we just return m.elements at 0, at 0. I mean, it turns out that, in fact, this 2x2 matrix isn't too much of a base case. It just makes it easier because we don't have to recurse any further. But you can actually do this without having the base case here, because technically when we splice, if we use the A as our cofactor, then we're splicing the first row and the first column, which leaves us with the D, which is the other matrix, which is, and the determinant of the D matrix, or of the matrix, the only D would be D, so A times the determinant of that is just A times D, and you subtract B times C. So we actually don't need to have the second base case there. Cool. So the base case is just if the number of rows is equal to 1, then you just return the element. And then we're going to have a character for the cofactor sign. It's equal to -1, or is equal to 1 to start, sorry. And then the float ret is equal to 0.0. Then we're going to iterate through each of the columns because we're going to clear across the first row, or expand across first row. So for unsigned int c is equal to 0, c is less than m dot calls, c++. Then ret plus equals cofactor sign, because remember we have to alternate it. So cofactor sign times m dot elements at 0 at c times the determinant of the splice mat, passing a reference to m, 1 for the exclusion row because we're expanding across the first row, and then c plus 1, and we do the plus 1 because we are counting from 0 in the loop, but 1 in the method. And then after that we have to reverse the cofactor sign, so cofactor sign is equal to negative cofactor sign. Then return ret. Okay, let's get an example here. Here we go. That's a good one. Okay, let me actually just leave this up for a second so I can refill my water. I've gone through 2 glasses already. It's just, damn it. It's just so much. I think we're actually done though after I test this, because this was all I wanted to really do. Alright, this matrix here. So we'll just get rid of all the matrices up here, and we'll just have the single one. Mat m is equal to matrix 3 rows, 3 columns, 7.0 float, 2.0 float, 0.0 float, 3.0 float, negative 15.0 float, and 0.0 float, 6.0 float, negative 4, 2. Print mat m, then print f. We're going to print the float now, printing determinant of m. Oh, I put an integer at the end. Should be 2.0 float. Negative 222, that is not right. Or is it right? I feel like this... What? Is... Wait, this is just straight up fucking wrong. God, this is the second time that we've used an example that's wrong. Because 7 times negative 15 is definitely not 3 times 2. So if you subtracted them, what the hell? Come on, people. Where are my quality math teachers on YouTube? Come on. Wait, did you correct it or something? Wait, why'd you... Oh, the fucker. Oh, it wasn't wrong. Oh, I feel bad now. I feel very bad now. This is just a thumbnail, okay. So it was negative 222. Attaboy. Alright, pretty cool. Alright, I am going to actually... I need to blow my nose and get some more water. And I'm just going to finish it right here. No cushy goodbye. But thank you for watching. Have a very happy Thanksgiving, or 23 more minutes of Thanksgiving. Finish your leftovers soon. Don't let them rot. You use them in sandwiches. Turkey sandwiches, especially with gravy, are a fucking slap. They are very good, and if you have a lot of leftover turkey, that's good for like a week. You could get a nice week of sandwiches, of fine meat for sandwiches, which is good. Yeah, all right, I'm done. My mouth is just becoming increasingly number and stiffer. Oh Jesus, this is bad. All right. I hope you guys enjoyed, and I will maybe see you guys tomorrow. I doubt it though. Probably Saturday then. I'll see what my schedule is. But yeah. I'll see you then. Have a good one.